Hello, my name is Jerome Rossignol. I'm an associate professor at University of Bourgogne. I'm working on microwave sensor and microwave imagery for industrial application. Today, I'm going to introduce our work about detection of organoleptic faults in wine by microwave sensor coupled with molecularly imprinted silica. This work is a joint collaboration between ICB Lab, CNRS, PAM Lab, Jules Guyot Institute, and SAYENS from Dijon.
First of all, let's take a look at the purpose of this research. Then I will move to the organoleptic faults to detect. I will also show our strategy for this project. For that, I will give you more details about the sensitive material we use, the molecularly imprinted silica, through the experimental setup. And last but not least, the results. The purpose of this research is related to the contamination in wine. I'm going to focus on a mushroom botrytis cinerea and its impact in wine, especially long-term keeping white wine. This mushroom is present across the globe. In France, the estimated harvest loss is between 15 to 40%. The economic impact is around 2 billion per year. The phenomenon is growing due to the climate change. Two molecules are linked to this mushroom and can be considered as contamination markers. The first marker is phenylacetaldehyde, an oxidation marker which is correlated with a mixed flavor of aged honey or overblown rose. Its aroma detection threshold in hydroalcoholic solution has been calculated to be as low as 1 microgram per liter. Early detection of this marker in wine at concentration under aroma threshold is required for efficient anticipation and proper œnological practice to protect wine from oxidation. The second marker, 1-octane free one, is associated with fresh mushroom and earthy of flavor. For example, a threshold of 30 nanograms per liter has been measured in red wine. The second marker is possible cause of cork 10 Gougeon in French, which affect 10% of bottles worldwide. Usually, the phenylacetaldehyde is detected by gas chromatography. The 1-octane is detected by GCMS, and these ex situ analytical processes need a sample preparation and are expensive. To detect these chemical species within wine, the research strategy is based on the following items. The process must be selective and in situ. This indirect sensor is composed of a sensitive material, a transduction, and an instrument. Molecularly imprinted material, MIM, are one of the most specific and selective materials used in analytical chemistry. They are biomimetic synthetic materials able to mimic the specific interaction between antigens and antibodies, hormones and receptors, or substrate and enzyme. MIM have the big advantage of being stable in extreme conditions of pH and temperature in comparison with biological material. Based on the microwave transduction, the measurement is quick and excludes sample preparation. The sensing method can be used with portable instruments. The previous work of this joint collaboration was focused on the pesticide detection. The target was a fungicide, Hypodium, detected in tens of nanograms per liter range. You can see here the synthesis of the molecularly imprinted silica and their corresponding controlled non-imprinted silica, NIS. To select the molecularly imprinted silica in order to integrate it within the microwave sensor, the following three steps were used. Step 1. Mist polymers are prepared at 40 degrees in a thermostatic water bath under magnetic stirring. The template molecule is first dissolved, then water is added, followed by the functional monomer and the cross-linker tubes. Finally, ammonium hydroxide or chlorhydric acid are introduced. The reaction mixture is left under stirring for 20 hours. The polymers are separated from the liquid phase by centrifugation at 10,000 G for 10 minutes. In order to remove the template, polymers are washed several times with ethanol until it's no longer detectable by chromatography. After washing, polymers are dried. NIS are synthesized under the same synthesis condition as those MIS, but without phenylacetaldehyde, the template molecule. NIS served as control polymers. Step 2. The tested polymers are suspended in a wine model. A stock solution of water ethanol with phenylacetaldehyde is prepared at 400 mg per liter. Three concentrations are studied: 20, 80, and 200 mg per liter. The samples are analyzed by gas chromatography mass spectrometry. Step 3. The selectivity studies are performed the same way as a batch extraction study. The table of synthesis shows the 5 candidates to detect the phenylacetaldehyde. Parameters are the functional monomer PATMS of APTMS and the aldehyde function of phenylacetaldehyde. Result of the batch extraction study is shown in the second table. The quantity of the adsorbed phenylacetaldehyde is expressed in function of the initial concentration. Each count of phenylacetaldehyde. Polymer 3 and 4 were kept for the selectivity study. The initial concentration for each of these molecules is 400 mg per liter. The partition coefficient, Kp, of each compound between the polymer and the hydroalcoholic medium is used to assess the selectivity. It is calculated using the following equation, where Ci is the initial concentration of the target compound, Cf the concentration at equilibrium, V the volume of the solution, and M the polymer mass. Phenylacetaldehyde is replaced by a mixture of competing molecules. Phenylacetaldehyde, benzaldehyde, 1-octane, 3-one. This value of partition coefficient between the initial solution and the polymer are presented in this graph. Both SL3 and SL4 gave high partition coefficient for phenylacetaldehyde in comparison with competing molecules. In the case of phenylacetaldehyde, difference between Miss SL4 and Nis SL4 is higher than the one between Miss SL3 and Nis SL3. Thus, Miss SL4 is selected in order to be used in the microwave sensor. The microwave sensor consists in a microstrip multiresonant design with a trapezoidal spiral. The experimental setup consists in a portable vector network analyzer, a personal computer with LabVIEW from National Instrument. The measure return loss of the circuit covered with mist represents the sensor. This acidity in wine is close to 4. To remove the risk of corrosion of the metallic line, the entire sensor is coated with PDMS, except the spiral. Sensitive material is deposited following a simple Dr. Blade protocol. Then this structure induces a temporal stability of the response. To remove the mechanical noise, the sample is moved by lab scissor jack. The sampling medium is a regular white wine from the Cellier des Dauphins. The measuring process consists in immersing the sensor into the sample. Total immersion is achieved by control with microscope cam. Different volumes of oxidizing elements in solution are added to the initial solution in order to increase the concentration through the chosen range. Measurement is performed within 1 minute after stirring. The concentration covers the range from 0 to 16 micrograms per liter. The concentrations are in x-axis. Figure shows the linear response at 2.4 GHz. First resonant frequency for these sensors with these sensitive materials in y-axis, with increasing concentration of phenylacetaldehyde. Molecularly imprinted-based sensors are thus able to detect phenylacetaldehyde in wine at microgram per liter level below the off-flavor threshold. The preliminary results on 1-octane 3-one are presented. The source of flavors of wine fruit is tested in a wine model, was ethanol. The concentration covers the range from 0 to 100 nanograms per liter. Figure shows the change of response at 411 MHz with increasing concentrations of 1-octane 3-one. On the figure, the response shows a good linearity through the concentration range 0 to 25 nanograms per liter. Above this value, the response has reached plateau. However, the complexity of the wine matrix needs to be taken into account in order to complete this work. To conclude, this work highlights 3 key facts. First, we propose an in situ process to evaluate the organoleptic faults in wine. This enables a rapid and real-time analysis to assess the level of wine oxidation. We also demonstrated a linear relationship between the sensor response and the phenylacetaldehyde concentration. This measured concentration range is under the olfactive threshold at the start of the wine degradation. In addition, we got a promising result on mushroom and earthier flavor in wine model. Objective is to optimize the wine aging and reduce the harvest losses. Thanks for your attention.